Hello, everyone, and welcome to today's webinar. Welcome to today's webinar. This is the fifth, I believe, webinar in our ASHRAE Technical Committee 6.7 webinar series. Technical Committee 6.7 is on solar and other renewables, and it sponsors this webinar series. So I'm Ana Maria Segunes. I'm currently serving as a membership and outreach subcommittee chair. And today we have the pleasure of having with us Dr. Costa Kapsis, who will be giving us a presentation on BIPV and the design and implementation of BIPV projects, and also present some real case studies. So just before moving into that, I'd like to also mention what we're going to have also a presentation at the end for the TC, but everyone who wishes to join TC6.7 is free and is welcome to register and participate in our activities. And the next committee meetings are going to be during the ASHRAE Winter Conference in Las Vegas from January 31st to February 4. And the meetings are in hybrid mode, so you can also participate online if you cannot be there in person. But going back to today's event, so I'd like to introduce Professor Costa Kapsis. Costa is he's a building scientist and an architectural engineering educator, specializing in sustainable building design. He's contributed into the design of over 30 net zero commercial and institutional buildings, and in the University of Waterloo, he co-leads the Climate Resilient and Intelligent Buildings Research Group. He is an ASHRAE and ASCE member and serves as an associate editor for the Journal of Architectural Engineering. Finally, for any questions or comments that you may have, you can leave a comment in the chat, and then at the end of Costa's presentation, we'll have a dedicated Q&A session to discuss the presentation and answer any questions. So, Costa, please, you can start your
Thank you, Ana
presentation.
Maria, and good morning, good afternoon, good evening to everyone joining us today, and thank you for the kind invitation. So as Ana Maria, let me share my screen here so I can set up my side. Perfect. There you go. Okay. So as Ana Maria mentioned, that today's presentation is on building integrated photovoltaic envelope systems, and we're looking from the perspective of how we can use the technology effectively to help us move closer to building decarbonization and electrification. And it is a webinar under ASHRAE Technical Committee 6.7. Before I start, I would like to acknowledge all the effectively authors and contributors to an International Energy Agency Task 15 that is focusing on building integrated photovoltaics. The work I'm going to present today comes from a Building Integrated Photovoltaic guidebook that is available open access and free to everyone because of the IEA. IEA is also has a liaison with ASHRAE, so effectively they're two organizations that work very closely in coordinating work. So effectively, the work I'm going to present is a concentration of work from 28 total contributors from 15 countries of a total 82 person months. It took us about 4 years to develop the guidebook, and I'm going to present part of that work. The learning objectives for today is, first of all, to understand what is BIPV and effectively how it comes into the game, into our building envelope and mechanical design of our buildings. We're gonna walk together through best practices for specific systems. Mainly, I'm gonna focus into two different building integrated photovoltaic systems. One is rain screen, which is very common, and the other one is rooftop PV. I'm gonna also present for our practitioners a robust decision-making framework that you can follow step by step, a total of 7 steps, in order to decide if BIPV makes sense for your building, new or retrofitting, where you're going to be allocating that piece of equipment, how you're going to be sizing it, selecting equipment, commissioning it, and so forth. And then at the same time, I will take the opportunity to present some successful case studies across the globe. As a first step, I would like to discuss very briefly what is building integrated photovoltaics, or in short, BIPV, for the folks that might not be familiar with the technology. So effectively, building integrated photovoltaics are building envelope products that effectively deploy photovoltaic technologies. So imagine they're conventional photovoltaic modules, solar panels, but effectively playing the role of a building envelope system. So they produce solar electricity, renewable electricity, but at the same time, they offer one of the building envelope functions, such as weatherproofing, exterior shading, and you can see here, for example, some of the key applications. So effectively, your BIPV can be your building roof that it generates electricity but protects your building from the elements. Also offers aesthetics. It could be your curtain wall system, right? That generates electricity, but impacts your HVAC loads, day lighting, electrical lighting, of course, occupancy comfort because it provides shading inside your building. It can be a solar shading device of your building facade. It can also be your rain screen, right? So effectively, today's presentation is not going to be discussing about the conventional solar panels, rooftop solar panels, or ground-mounted solar panels. We're talking about a building envelope element that is called BIPV. So effectively, these are electrically active envelope systems. Because of that, BIPV need to comply with our building codes, with our electrical codes, and fire safety codes. And therefore, as you will see, the process might be a little bit more complex than just a conventional PV system or conventional building envelope system. And that is why it's important to engage early on our architects, mechanical engineers, and electrical engineers into the design of the system to produce something that will be optimized and long-lasting. Now, when it comes to BIPV, one of the major, I'll say, selling points is that besides that is effectively an electrical/mechanical equipment, it also enhances the aesthetics of the building. So effectively, what we have done in the past 2 to around 3 decades is that we have taken glass technologies such as printing, coating, and etching, and coloring of glass, and we have implemented these technologies into solar modules. It could be in the form as you see dots, but it could be a fully colored, effectively coating or etching that prohibits the exterior view from seeing the solar cells. So effectively, BIPV is an envelope technology that effectively, only if you know that is there, you will understand that is a solar active technology. Most of the times is hidden on, on an everyday, effectively, pedestrian or user. So you can see here, for example, how we can change the color from and transparency of the glass, right? In some cases, the solar cells are fully covered, and in some other cases you can have an effect where you can see partly the solar cells and of the solar cells, sorry. And as you're applying the coatings, prints, or etching, of course we're shading the solar cells, and you can see effectively how that shading effect has an impact on the efficiency of our BIPV system. So as I said, BIPV can come in any color, shape, and texture, so we can texturize also glass. Someone will say, but why? It could be for aesthetic purposes. It could be because we would like to reduce solar reflection, especially on a large glass facade, to minimize, let's say, veiling glare to the buildings across the street or to our pedestrians. And therefore, it's a fully customized product if we wish. Of course, as any other product, as soon as we're looking into customization, that will affect the module price and the price per square footage. So you see here some coloring techniques where effectively your solar panels that are playing the role of the roof or your facade could be from terracotta to fully white to black. In some cases, you can choose to see the solar cells or fully cover your solar cells, all the way to printing technology where effectively you can put your image or a poster on your facade or a piece of art where effectively this is a solar active surface to generate electricity. So knowing this basic attributes and characteristics, let's walk through the two basic systems for today that we see in the world of buildings when it comes to BIPV. And that will be first the rain screen and some case studies, followed by solar BIPV roofs and some case studies. So as a first step, what I would like to do here is walk you through the fundamental design of a BIPV rain screen that doesn't go far away from the conventional design of a conventional rain screen. Now, in summary, what is the main characteristic of a rain screen? A rain screen is effectively an element of your envelope where effectively there is a cavity behind your exterior cladding that allows a discontinuity between your exterior cladding and your inner envelope system. And that, of course, reduces capillary effects or drains any water or any penetration of water into your envelope, keeping your system and your wall and your roofs dry. Okay, so if we start from construction of a BIPV rain screen from the innermost to the outermost layer, we have our building structure. Here's a backing wall, for example, that is the load-bearing wall. We apply the water and weather proofing and air proofing of the surface if that is necessary. That could be a self-adhering membrane, it could be sprayed applied. Then we attach the thermally broken brackets that will be holding our rain screen system and railing, where upon which we'll be installing our BIPV modules. Then we apply our insulation, which is the green layer that you see. And of course, the thickness of the insulation depends on the conditions and our building codes. And then we create a little cavity. That cavity is very critical, not only for draining water, but also allowing air to come inside the cavity and cool down our BIPV modules, and therefore enhancing slightly the efficiency of our system and keeping it into, cooler temperatures than if it wasn't ventilated and sealed cavity. Also, the cavity, typically we want to be around 3 to 3.5 inches or larger. That allows airflow. Is also used for draining purposes, right? For the folks from outside the United States and Canada, 3.5 inches, about 80 millimeters or more. And then we have our vertical effectively frame and our horizontal frame where we attach either through connectors that are on the back side of our BIPV modules or through pressure plates our exterior cladding. Typically, for the building scientists of today's presentation, you might be familiar with other materials that in conventional construction is a precast concrete. It could be an aluminum or a composite panel. In this case, we're using electrically active envelope modules, right? The BIPV modules. The difference with these modules is that they come with a junction box on the back and two cables, a positive and a negative cable that effectively anticipates the DC electricity. Most of the times we connect these modules in series in a daisy chain effect. And then we bring through a dedicated penetration through your envelope, that cable inside our electrical system to connect it to an inverter. And the job of the inverter in the electrical room is to take the DC electricity from our modules inside our building and invert it to AC, which is the type of electricity we're using in our building, right? So knowing now the basic principles, there is a couple differences, conventional system, and the major difference here is that we need to be able to have railings where effectively we run our cables to keep them safe. And also typically when we build a rain screen of that system of BIPV, what we tend to do as a good advice is that the first 2 meters from the ground should be effectively non-active modules, right? So dummy modules, because these are the modules that will take the impact, physical impact from pedestrian, from a truck, potentially, and then you don't want to damage your electrical equipment. And from the 2 meters and above, any stories above that will be electrically active. Okay, so here you can see the modules being like color blue, but effectively they can have any color, any texture, as we'll see through the following case studies. So in the next couple of minutes, I'm going to walk you through 4 curtain wall case studies across the globe, and I'm going to start from the warmest climates all the way to the coldest climates. As a first example, I would like to bring up a building that is a double skin facade, which is effectively a type of a rain screen system that was installed in Grenada, Spain. This is a very arid and hot and warm climate. It's 3B based on ASHRAE climate zone. And in this case, as you can see on the picture on the right, the solar modules are semi-transparent amorphous silicon. So effectively, they let some of the sunlight to enter. On the back side of the rain screen, we have effectively opaque envelope and windows. So effectively, they allow some sunlight go through, and they play, of course, the role of a shading vertical device. The cavity here is about 0.5 meter, significantly larger of 3.5, of course, or 80 millimeters, 3.5 inches, and that is because they were used for natural ventilation purposes. The specific building, it was a new construction, and it's a hub of interdisciplinary research between health, university, and industry professionals. The BIPV rain screen that you see on the left side is a 550 square meters or 5,500 square feet of double skin facade that uses 2 color amorphous silicon glass, and that is more of an architectural purpose, where effectively we use the solar modules as pixels to create an architectural look. The system was designed effectively to supply 100% of the electricity demand for the lighting loads of the building. The rain screen is a very straightforward system, so you can see that there are thermally broken brackets that are connected to the main structure of the building. That structure here is what contains your weather barriers and thermal insulation, of course. And then there is an exterior screen, your rain screen, that effectively through pressure plates that you can see in details hold the solar modules in place. These solar modules on the back, of course, you can have opaque wall or windows, and therefore they play also not only the double skin facade function, electricity generation, but also function as a shading device. Now, in somewhat similar climate, we're moving to a retrofit rain screen in a mall in Rome, Italy. Interestingly enough, that was a 1970s building. As you can see, the building on the left, that was a building pre-renovation, where effectively the engineers, the envelope engineers, and the architects coordinated to create a building-integrated photovoltaic rain screen that will cover the total of all the facades east, west, and south of 10 stories high. The renovation took place in 2019 and incorporated, as you can see, not only BIPV modules, but also shading devices. Now, the interesting thing here is that the architects tried to create a pattern where they made the BIPV modules almost invisible to the pedestrians. So effectively, if you walk in front of that building, you will see and you will think that these blue sections are the windows, while the louver part is the spandrel, but it's the other way around. So effectively, the blue part is the spandrel, as you can see here. And right above, we have an exterior shading device, controllable shading device, that provides shading on the windows that are located behind. So effectively, that was a 145 kilowatt BIPV system that was deployed on the spandrel part of your rain screen. Okay. That effectively produce about 140 kilowatt hours per square meter per year, which is 137 megawatt hours, powering about 10% of the total electricity demand for this mall. Now, moving to colder climates and 6A ASHRAE climate, we're in a city very close to where I'm located right now. This is London, Ontario in Canada, where effectively it's a university building, it's a college building as part of an electrification of the campus. This was a new building, as you can see on the left. And the interesting part with that new university slash energy center was the complexity of the facade. So as you can see on the right picture, every surface that you see here is a solar panel. Some of them are so electrically active and some of them are dummies. And the decision here was taken with a coordination with the electrical engineers to optimize the performance of the system. There are several different sizes of modules, customized modules. And then you can see that interesting blue hue. Effectively, all the modules have the exact same color, but because developed based on physical vapor deposition coated glass, what happens is that there is a specular reflectance and angular reflectance, and as you move, every module looks like it's changing its colors, almost like fish scales, right? So that creates a very interesting aesthetic from an architectural point of view. Now, if I move on the right side, as you can see, we have all our envelope components. We have our structure, we have our insulation, we have our thermally broken brackets that hold the complex drain screen in place. You can see a cavity behind. You have your junction box and the optimizers. In this case, we use optimizers because we had to optimize the output of the system, and that optimization challenge was due to the complexity of the geometry of the facade. With that specific system, initially there was a concern of high cost, but when the engineers and the client run a cost-benefit analysis, they found out the BIPV facade made sense to be installed on every side of the building, including the north-facing elevation, which is an interesting approach. The total system is able to generate 123 megawatt hours per year on average, and that covers about 18% of the project's near-term power requirements. And the university right now, the college is looking to deploy a rooftop PV system to meet 30% of electricity demand for the center. Will remain on a similar climate, where now we're moving effectively to Midwest in Winnipeg, Manitoba. Again, we're in Canada. We're in an even colder climate, 7A ASHRAE climate zone, where again, we're looking into a college building, educational building, where it's an incubator. And the intention here was the client wanted to create a building that meets the carbon neutral performance targets of 100 kilowatt hours per square meter per year. So for that climate, that is a very efficient building because this is a heavily heating dominated region of the world. As you can see, the entire facade is building integrated photovoltaics. These are the golden modules that you can see, very similar style to the blue ones that we saw. So effectively very similar coating, but this case, the client decided to go, and architects to go with a golden look. The rain screen is a total surface area of 710 square meters or 7,100 square feet around. And the interesting part with that is that the design of that system started in the early stages in the preliminary design, where effectively there was a strong coordination between engineers, architects, and the client for modeling, testing, and also mock up that unique system. You can see that there are several different sizes of modules, well coordinated with your curtain wall or punch-in walls. windows. And as you can see here from a top view, you have the thermally broken brackets. Sorry, my apologies here. This is the interior part of the wall. Insulation between. In most of the cases that I've shown you, the insulation is mineral wool, and that is to have enhanced fire safety requirements. And you can see that the cavity is ventilated and junction box with cables that run through railings, through our facades. Same modules with the same orientation, same size are wired together and then all wired in series. And these modules are wired in parallel with another string. That final DC cable comes inside the electrical room connected to electrical equipment and inverter to transform solar electricity collected from your facade to AC usable electricity in your building. Effectively, oops, my apologies. This system with the rooftop PV produces about 70 to 80% of the daily building electricity requirements for that college building. Now, moving to another very common building integrated system, we're moving into the roof BIPV roof systems. Here, the principles are very similar. You can see the complexity of the structure underneath, where you have your rafters and your joints. Before that, of course, you have your structure and your weatherproofing, waterproofing, which is the primary water barrier. You have your racking system, where it comes and holds in place your modules, your BIPV roof modules, and then of course creates a cavity that allows air freely to move underneath your BIPV shingles, right, or panels, whatever you like to call them. That cavity typically is about 3.5 inches, again 80 millimeters or more, to enhance natural ventilation. There is no need most of the times for mechanical ventilation, and you can see here the top roof reeds that allows air to go through and naturally ventilate using effective stack effect, right? Interestingly enough, for this climate, what we had to do is that for colder climates, you might want to use snow guards effectively to prohibit snow falling and sliding down. You have to incorporate your gutters, and we've seen installations I will show you later on today, some case studies where we had an integrated gutter as part of the system. You see, you can incorporate, depending on the geometry, some dummies that have the same color and texture as your BIPV modules. You need to include wiring control conduits to run your cables safely. And in all cases, in all climates, is very, very important is when you have a cavity like that, an opening like that, to use an insect screen. The insect screen here is used to avoid buildup of, let's say, a wasp nest or birds or other critters nesting under your roof and therefore impeding the airflow and potentially creating hazard for fire. Okay, so upon these principles, your BIPV roof is your secondary weather barrier, where it effectively deflects and drains snow, ice, and water. And if any water penetrates through your BIPV modules, you can have your self-adhere membrane that plays effectively the primary weather barrier that deflects and drains the water through the cavity to the gutters and away from your building. Upon these principles, I'm going to walk you through, again, 4 case studies across the globe, starting from the warmer climate all the way to the coldest climate. This first case is a heritage complex that is located near Venice, Italy. This was a deployment and replacement of terracotta tiles with BIPV roof for the entire section. As you can see here, effectively, the BIPV modules come and click together, almost fist scales, and then there is a self-management cable system. You can see that the racking system is on the back. which contains also insulation. In this case, there is also a vapor barrier on the warm side of your insulation, which is the outermost layer, and of course water and air barrier to prevent vapor, rain, and air to enter your mass timber roof of your system. We saw one of the multiple buildings that the system was deployed. It's a 183 kilowatt system, total of 400 square meters of roof that produces about 211 megawatt hours per year. Another similar system remain in EU and Bolzano, Italy, which we're moving into a 4C, a little bit cooler climate and milder climate zone than Venice, where effectively here we use, this is a gear garden where they deploy a flexible amorphous silicon thin film modules on an aluminum backseat. So you see here you have the corrugated aluminum roof, and we deployed flexible amorphous silicon thin film that are 9.2 kilograms per strip. You can see the strips here. These long BIPV modules are incorporated in the south tilted roof that is about 25 to 35 degrees of slope, and it's a radiant roof pattern. It covers about 168 square meters, providing about 10.4 kilowatts of nominal power, and generates about 13 megawatt hours on an average year. The project was a retrofit and was completed in 2010. And the idea behind that retrofit was educational to the students, but also the community, but also move towards the electrification, decarbonization of the kindergarten. As you can see here, the construction is very simple. Effectively, the insulation, all the weather barriers and air and vapor barriers are deployed on the horizontal roof, and there is an elevated structure that creates a BIPV roof that creates the spiral effect into what looks like a building integrated photovoltaics, and then that roof, of course, is vented to cool down the modules and avoid overheating. Finally, an interesting project that combines both facade and BIPV roof. So this is a fully integrated building integrated photovoltaic system where effectively the balconies, facade and roof is building integrated. This is in Steinbach in Switzerland, which is effectively near Zurich. This is a multi-story residential building that hosts 10 apartments with a view to the Lake Zurich, where the architects with the electrical engineers were able to coordinate and come up with a single module design of 1,300 BIPV modules. The smaller modules that you see here are dummies, effectively. They don't produce any electricity, but they're to create a uniform look. The entire facade and roof is able to generate enough electricity to make this building self-sufficient. In addition to that, there are seasons, especially in the summer and spring months, where effectively the system produces more than the electricity that the building is needed, and therefore they have deployed a 10 kilowatt hour stationary battery for one electric car to effectively store the excess of generated PV electricity. And of course, here the architects create a very unique look in coordination with the envelope engineers and electrical engineers that they chose a specific brown cladding, that is made out of ribbed cast glass that does not show any solar cells on the background. Now, if we go into the cross-section of the system, you can see that you have your structure, your thermally broken brackets with your mineral wool insulation. You have your L-profile support rails, where effectively the BIPV modules and roof are clicked with a proprietary system on the railing and locks in place. While they do that, at the same time, they have to electrically wire the modules with each other. And then, of course, these DC cables come inside to connect to the inverter of the building in the electrical room to produce the AC electricity that is being used in the building and charging the battery and the EV. Finally, in cold climate again, or colder climate, we remain in Europe for a heritage building downtown Copenhagen in Denmark. This is the 5C climate. There's a typo actually here. It says new, but this is a retrofit, where effectively, as you can see on the left, the initial building that was built in the beginning of the 1900s had a corrugated metal roof that start leaking and creating issues. And then through an incentives program, the building owners decided to renovate the full building, increasing insulation, air tightness, changing windows, but also putting more insulation on the roof and incorporating BIPV modules. In this case, there were the renovation took place in 2013, and the roof is functional since then. The corrugated roof was effectively removed and replaced, and then in its place, I was put new corrugated roof with structural connections, your weather barrier, effectively that waterproofs the corrugated roof. That is your primary water barrier. And on top of that, there was a railing system that was holding your BIPV modules in place. You can see that they're integrated gutters into the system, but at the same time on the back, there is 80 millimeter cavity that allows natural ventilation and cooling on the back of the modules that vents on the ridge of the roof. This was a 20.3 kilowatt system, about 108 monocrystalline silicon modules. About 60% of the roof was covered with BIPV modules. The rest were dummies that create the same look. So effectively, the roof is 140 square meters and covers about 20% of the building annual electricity consumption. Now, we've seen two very fundamental applications of BIPV. We've seen rain screens and we've seen BIPV roofs. Of course, you can also deploy BIPV as balcony railings, as shading devices, as skylights, curtain walls, and so forth. Effectively, any building envelope system that has access to the sun can be replaced by a BIPV equivalent system. Okay, so the next question that comes, and many of you might have that question, especially for the practitioners and clients that start being interested in that technology. This is the mature technology that you can find in most of the countries at this point around the globe. There are available products. Is how do I know if BIPV makes sense for my project, new or retrofit? So effectively what we have done in collaboration with several countries and practitioners across the globe is to come up with the map of a decision-making process framework on when and how we take steps to decide what is the appropriate solution for us. Does it make sense from cost effective? Does it make sense to incorporate in our project from a project management, but also from a sustainability and energy generation? On the top side of the figure, you will see that this is the building design stages where we start our preliminary design to a schematic design, to design development, and then construction document, building permits, bidding, and construction administration of your building. And that applies, of course, for new and retrofit buildings. And at the bottom, we have a line, 6+1, total 7 BIPV design stages that you can take, and we can create the lines that you see here are showing the affiliation, how they impact the different design stages and construction stages of your building projects, starting from why and does BIPV make sense for my project, all the way to BIPV design and deployment, sustainability analysis, and cost-benefit analysis. So I'm going to walk you through this 6+ one steps. And then we're going to show you some quick examples of calculations on how you can perform your own quick assessment. As a first step is, why should we use BIPV? And how do we convince potentially the client or the building owner or the asset management company to agree to deploy that technology in their new or retrofit building? There are different ways of pitching and different reasons why we should do BIPV. First of all, there is energy generation and savings potential. Instead of doing just, let's say, your roof and then pay an additional cost for your rooftop photovoltaic solar panels, you can kill two birds with one stone by having a BIPV roof that is both your roof and your solar system in a single solution that produces an energy and minimizes or reduces your energy consumption and helps towards electrification, decarbonization targets of your building. In many countries, we start seeing regulatory compliance where effectively we're expected to have some local photovoltaic generation on buildings or communities, and BIPV can play a big role in that. Interesting enough, for our architect friends, there is enhanced aesthetics. BIPV is a very new, and I will use the word sexy, building envelope product that can come in different shapes, textures, and colors, and therefore can be used to enhance the aesthetics of existing or new buildings. In Europe, we see more and more where the deployment of BIPV can be reflecting to the property value and selling and rental prices. When it comes to more of office spaces, institutional properties, corporate green status or certifications under green standards plays a role. I will give you an example. The Green Building Council carbon neutral standard dictates that at least 2% of your generation should be covered by BIPV, and therefore you meet this requirement by deploying BIPV. And then, of course, depending on the jurisdiction, country, or region, you might have renewable energy credits and incentives that we'll see some examples later on today. Now, if some of these things apply to you, then you can very quickly move to the next steps. The first step is to assess your building site. What you see here on the right side, top right side, is an example of a BIPV potential heat map for the city of Toronto in Canada, where effectively around you can see the orientation of your facade, so south, southwest, northwest, north, and then the circles that you see here, the homocentric circles indicate the slope, right? 0 is a horizontal roof, 90 is a vertical facade, anywhere between is a slope of a shading device or your roof. Of course, for Toronto, located in the northern hemisphere and relatively high latitude, about 45, you'll see that south-facing, southwest to southeast facing is the BIPV orientation that has the highest potential, anywhere between 10 degrees to 60 degrees of the slope, right? And then as we're moving away from south, you'll see that generation reduces, and you see, that, of course, that the lowest potential generation happens on north facade. Now, that figure here can give you a quick understanding how your building is oriented and what are the potential surfaces that you should be looking into to deploy BIPV technologies. Of course, this is for an unshaded facade, let's say, or a roof. And then many cases you might need to deploy a solar access study. This is a solar study that we perform here at University of Waterloo for a high-rise building downtown Toronto, where effectively we assess all the 4 facades, and we found the potential, of course, of its facades on deploying BIPV curtain wall system. Beyond that, is very, very important in these first stages to coordinate with your utility to ensure that you meet any utility requirements in terms of interconnections and injection of electricity into the grid and your transformer, local transformer. In some cases, you should be looking into zoning bylaws Depending where you are in the world, in some cases, you might be protected by laws or bylaws associated to access to or the right to the sun. So effectively, if your facade is a BIPV, then your neighbor is not allowed to block that facade and reduce, of course, generation. In some cases, you might need to look into specific BIPV products if it's a heritage designation buildings, such as the terracotta BIPV modules that we saw before. Now, as soon as you determine all these quick aspects, solar availability and access analysis through very basic simulation tools that are available to all of us in our practice can give you a quick understanding which are the surfaces with the highest potential. As soon as you identify the surfaces with the highest potential, the next step is determine what is your generation scheme, your target. Are you installing BIPV because you want to partially offset your consumption? Are you looking into self-consumption targets, which means you want to consume as much as electricity, solar electricity you produce in your building, or are you okay exporting and selling some of that into the grid, right? Are you looking into net zero performance targets, which means are you looking to generate as much electricity as your building consumes in a period of a year? Or are you going beyond and above just net zero energy and you're looking into carbon neutrality, where effectively you need to generate more electricity than you consume per year in order to offset the nominal emissions due to construction of your new building, such as embodied carbon, right? So when you determine these aspects, then you need to perform your very quick hand calculations by just using a spreadsheet on how much potential I can generate, how much my building will consume, how much I'm offsetting, how much more do I need, and do I deploy BIPV only on my roof, or do I look also deploying BIPV on my facade, south, east, west, and so forth. Now, you can take, as soon as you have a rough understanding, this is where effectively you come into your design thread and you bring in that knowledge and you start coordinating with your envelope, electrical and architects, electrical engineers and architects and mechanical engineers to start effectively going deeper into the analysis. And this is where effectively you need to take the extra step and be more specific into your location and start accounting for shading, soiling, self-shading of the building, to understand a little bit better what's the installed capacity and energy yield for your system. This stage you start looking into potential products, potential electrical solutions, envelope solutions, and so forth. Interestingly enough, when it comes to that step, we have our handbooks. So effectively, HVAC applications, chapter 36, and HVAC systems and equipment, chapter 37. We have deployed all the necessary calculations that you need to take in order to select equipment, size equipment, and very quickly assess potential generation. Some of which we will see as an example later on today. Now, almost near last step is to develop your BIPV design system, where effectively now you start coordinating with all the disciplines to select your modules, mounting system, string arrays, your inverters, and of course, at this stage, you have reached far enough to apply for utility interconnection, which is very important to coordinate. This is not, when it comes to engineering, of course, in BIPV, we need to start also looking into potential cost-benefit analysis, business models, and sustainability. At this stage, you can assess your non-return energy payback time. We have in the BIPV guidebook that is available and open access to everyone, as I mentioned before, environmental footprints, impact in terms of circularity, and what's the life cycle cost analysis, including maintenance and reuse. In many cases, the capital cost might be very high, and therefore at this stage, you need to start looking into different business models. Depending on the jurisdiction you are in, the province, state, or region, you might have a feed-in tariff, where effectively utility will buy your electricity at different rates at which you're buying electricity from the utility. Net metering, which means that you're buying and selling electricity at the same rate. You might be utilizing power purchase agreements, which some of you might be familiar through the net metering systems. And then, of course, we have a new approach that is BIPV as a service. Now, before I'm gonna move, there is a mistake here. The bibliography appears here, so that should be a slide at the end. But effectively, before I jump into a quick example to show you how you can perform your hand calculations or spreadsheet calculations, here's the references of all the work that I presented through the BIPV guidebook. If you're looking into ASHRAE design chapters associated by BIPV, chapters 37 and chapters 36. There is a BIPV validation application that is open access to everyone that I'm going to walk you through very quickly today. And then there is a standards report in case to understand what are the standards that apply for products and systems in terms of electrical codes, building codes, and fire codes. Now, one last thing here before we complete this presentation is some BIPV back of the envelope calculations. So you might be familiar, these are equations from our handbook. So effectively, there are two parts that you need to calculate. First, you need to calculate for every time step of the year, if you want to, the PV temperature. And by knowing the module temperature, you can calculate the potential solar generation of your system. You will need some technical information inputs. You will need your electrical efficiency of your modules and the power temperature coefficients. Don't worry, these are typically available from the product manufacturer. So if you go to any BIPV module manufacturer, you will find this information easily available. And of course, because we'll be running, let's say, an annual analysis or a monthly analysis, depending on what you're trying to do, you will need hourly ambient air temperature, incident solar radiation, wind speed at standard height, which is effectively what we call a typical meteorological weather file will do that job. We also bring into some equations some of the coefficients. These are empirical coefficients, A, B, and delta T. I'm not going to walk into details what A, B, and delta T function. What you need to, what's their role, but what you need to know is what is the kind of system you're using. Are you using a BIPV with a good rear ventilation, let's say 3.5 inches or more? Then you'll be using these coefficients. Are you using a double glazed BIPV in terms of a curtain wall? Then you'll be using this coefficient, or triple glazed, right? So depending on what kind of a system you'll be using, you'll be deploying these coefficients in the equations on the left. First equation calculates operational temperature. Second equation calculates power and therefore energy generation. So for a single time step, and then of course you'll do the same calculations for a full year, right? We have here an example that also appears in our handbook where you have a rain screen. You can see here rain screen, your insulation, your cavity behind, and of course your structure and your BIPV cladding. In this case, we have 100 square meters of a BIPV facade, and we want to calculate what is the power generation under 900 watts per square meter, 25 degrees Celsius temperature, and wind speed of 2 meters per second. By the manufacturer spec sheets, we know the module efficiency is 18%, so that could be a color BIPV module, and the temperature coefficient which is specific to a product given by the manufacturer is minus 0.5% per degree Celsius degrees temperature. Now, this is a cavity. We don't know what is the thickness of the cavity from the architectural drawing. So in this case, we can assume a medium rare ventilation, and we'll be using the coefficient of the table that we see from A, B, and delta T associated to medium rare ventilation. If we plug in these values, A, B, and delta T into our previous equation that calculates the temperature of the module, the outdoor temperature is 25 degrees, surface area is 100 square meters, solar radiation is 900 watts per square meter, our temperature coefficient is minus 0.5%. So we plug in all our values, and if we do our calculations for that given moment on time at 900 watts per square meter and 25 degrees outdoor air, the module temperature, surface temperature is going to be at 67.5 degrees Celsius or about 154 Fahrenheit. Now we know the temperature, we take this value and we plug it into our equation where it's TPV. We know the coefficient temperature from our manufacturer. We know the efficiency, 18%, and we assume a system efficiency, including the inverter, about 85%. This is for losses, associated to electrical losses, debris on your roof, let's say, or your facade, and so forth. You perform your calculations, hand calculations. So at that given moment, your 100 square meters of your facade rain screen will produce 10.8 kilowatts, assuming that for that 1 hour, the sun and the irradiance remain constant, then that will be 10.8 times 1 watt hour, 10.8 kilowatt hours for that given time step. And you perform that for every time step of the year. So I will stop here. Again, if you need to know more information, please look into our references. And before I pass it to Ana Maria, I have a quiz for you. If you want to reach out, that is my email. By all means, reach out. I'll be happy to discuss further. Back to you, Ana Maria.
Yeah, thank you, Costa, for the great presentation. I'll make a very fast presentation on ASHRAE, the technical committees, and how you can participate. So ASHRAE has 4 types of committees: the technical committees, task groups, technical resource groups, and multidisciplinary task groups. So the task groups and the technical research groups are formed for a specific concern in mind. Multidisciplinary task groups are temporary groups of several committees together. Today, I'll just talk about the technical committee, which is what the TC6.7 is. So we have 3 types of memberships: voting, corresponding, which is non-voting, and providential. Corresponding, which you'd be in the first, I think, 2 years of your membership, the providential corresponding, and then you move on to corresponding. And if you want to participate more on the TC, you can also become a voting member at some point. So TCs are formed through volunteers, and they come from different facets of our industry. So the only thing really needed is an interest and willingness to help improve the work of the committee. Yeah, so anyone is welcomed: manufacturers, researchers, utilities contractors, architects, engineers. Move on, please, Costa. Yeah, so here's a very basic structure of a technical committee. So the main work happens through the subcommittees. So we have 4 main subcommittees chairs, and then some TCs have some extra ones. The handbook revises and writes the ASHRAE handbooks that are consistent with the TC scope. We have the research subcommittee that identifies the research needs and develops proposals and monitors progress on research projects. And the program subcommittee, which is suggests and proposes topics and sessions for the ASHRAE conferences. And the standards subcommittee that identifies needs for standards and prepares proposals. Another subcommittee, for example, is also the outreach subcommittee that is for TC6.7 has, for example. Move on, please, Costa. So what about TC6.7? TC6.7 focuses on solar and other renewable energies. So all equipment, processes, and systems which collect, convert, store, and utilize solar energy and other renewable energy sources. There's different, here I'm showing the website of the TC, so you can go in, you can see past sponsored programs through TC6.7, research topics, and also there's the list of the past webinars and other links that you can see to follow the TC activity. And here I'm showing the LinkedIn and the YouTube page that we have for the TCs. So all the previous webinars that were done are recorded and uploaded on YouTube for you to watch on demand. Next slide, please. And why would you participate? So why participate in an ASHRAE TC? So you can have direct influence on industry standards and guidelines, give your perspective and share your experience, have access to cutting edge knowledge and research and what's going on in ASHRAE and in the industry generally. And also engage, of course, with professionals within the field worldwide. It's a great also networking opportunity and meet different people from different parts of the industry. And how do you participate? Here I'm showing, if you click Costa, I'm showing the pieces. So you go to the ASHRAE website, which is shown at the top. You go under communities and then technical committees, and then you can just click and apply. It's a form. It's free for everyone to use. You don't need to have an ASHRAE membership to participate in the TCs. And next slide, please. So, and then the is, as I said previously, it can be in person and it can also be remote. It's usually remote. It's during the TC meetings or during the winter and annual conferences of ASHRAE, and they're in a hybrid mode. The next one is, as I said, in Las Vegas from January 31st to February 4. And it's open to the public. There's no cost and there's no need for a conference registration to participate in the meetings. That's it, and I hope to see you in our next meeting. So going back to our Q&A, I guess, Costa. So we have some questions here. Let me go through them one by one. So first, Janice Means is asking, how does the colored glass affect the transmission?
So always depends on the color of the color. Sorry, the color of the film, but also the coverage. So let's talk about colors that cover fully the solar system. You will not be able to see them. Of course, that typically blocks part of the visible spectrum, but still allows the near infrared to go through. So effectively, if we had, let's say, a conventional panel that was 22% efficient, and then we covered it with a fully white, that will drop about to 18% efficiency. Interestingly enough, and this is more of a rule of thumb, and it depends on the technologies also of the color that we apply. There are different technologies of coatings. The darker the color, the lower the efficiency of the module.
So Edward Amoako is asking, has there been any implementation of BIPV in Africa?
I believe yes. I try to remember. I've seen some projects in Morocco and Algeria. I do not know. I know there was a potential project a couple of years ago, but I don't know if it happened in South Africa. But yes, I mean, it's less common. Also, I'm wondering if because also less available products in Africa, but there are a couple countries that we've seen implementation of BIPV, and typically these are either for universities, colleges, or government buildings.
Didier Theveronard is asking, PV projects typically require periodic servicing to make sure that the PV modules are working properly. Are there issues with difficulties of accessing the panels, replace them, or do IR imaging, etc.?
That's an excellent point. So effectively, in terms of maintenance, the maintenance is very similar to conventional PV. So effectively, there should be inspection, and depending on the jurisdictions, there should be an inspection on your building envelope too, right? So you need to inspect your building envelope every 5 years to ensure that things will be staying in place and will not flying away. So more and more, we start deploying drones through infrared thermography to understand if there are any modules are failing. Of course, the higher the taller your building, the more challenging it will be to go up and change the modules and do repairs. Typically, the inspection can take place at the same time as when we're cleaning a facade of a high-rise building, potentially. It could be definitely more expensive to maintain if there is an issue and more challenging. Nevertheless, based on our experiences, we have very minimal maintenance. And interesting enough, most of the maintenance takes place in the inverter side that is located in the electrical room. This is the component that tends to fail the earliest and most common, and it's not your BIPV facade or roof. And then typically when we have damage of BIPV, it's happening either on the roof surface, which is relatively accessible, or on the ground floor due to impact. And therefore, again, it's easy accessible. Or graffitis, let's say, vandalism. Some cases we had projects in Europe and Canada where effectively it was easy to go and change, the modules. The higher you go, potentially less impact is apparent, and therefore they can last longer, if I may say. Again, all that depends on the region you are. If you're in Florida, for example, where you have hurricanes, it's going to be a different story.
Yeah. George Rajunis is asking, can we appreciate the combined use of BIPV systems with new windows that come with inherent PV capabilities, such as PV fenestration with this design?
I'm not sure if I understand. Are we talking about BIPV windows, or are we talking about windows and BIPV products that are opaque? Because you can maintain your regular windows if you want, and use another shading device like the project we saw in Rome, and then deploy BIPV on your cladding. But another way of doing it is, instead of having exterior louvers to shade your windows or your transparent curtain wall can be your BIPV product. And therefore, you use BIPV solar cells as a shading device, and at the same time, you generate electricity. These are less common and tend to be a little bit more expensive products. So we've seen some projects, and we have in the guidebook several projects on that, but they tend to be a little bit more on the higher cost side, but still something you can do. And we're expecting, because glass is a very common and dominant material in modern architecture, these products to drop price as we go. So effectively, scalability drives the cost effectively, and standardization. I hope that answers the question. If the question is, how do we do it? How do we incorporate the BIPV curtain walls or skylights? And just because of the limited time of today's presentation, I did not present it, but if you go in the BIPV guidebook that is open access and available to everyone for free, developed by International Energy Agency, you will find the technical details that you need as a mechanical, envelope, or electrical engineer to deploy, size, and design the technology, including case studies. I hope that answers George's question.
Yeah, if you want, George, you can add some the clarification if you didn't get the answer you're looking for. I also added a link for the BIPV guidebook if anyone is interested to go take a look. Then we have from Zalalem Abebe, are there any commercial or institutional buildings that use liquid water-cooled BIPVT systems to harvest heat from building energy use? I'm aware that some net zero institutional buildings in Canada utilize air-based BIPVT systems.
Well, I'm not familiar with commercial institutional buildings that use water-cooled BIPVTs. I've seen it in the context of research, maybe a demonstration of the technology. But as far as I know, I haven't seen in a building. Maybe someone else is a little bit more familiar with that application. But I am very familiar with the air-based systems, and that is something we have seen a lot in Canada and Northern Europe.
There's also one comment from Veronique Delille. She has some answers on. She added a link on that question for IEA Solar Heating and Cooling Task 73, where they have some information on that. So.
Perfect. There you go. Thank you.
So Tower ASHRAE, sorry for the pronunciation of the names if I'm doing them wrong, but by the way, in general, for 1 square meter of available empty area, how much electricity can be generated by a BIPV, and how much it is more or less compared to a standard photovoltaic solar panel?
Oh, that is not a single answer to that question because it depends on your location, geographic location, where you are across the globe. It depends on your facade or roof orientation, if you're facing south or if you're facing north. It depends on the slope of your system, right? Does it accumulate snow? Is it the roof? Is it at 30 degrees? Is it vertical? Is it horizontal? Are you in, let's say, Rome? Are you in Berlin or are you in Oslo? So depending on where you are, the generation varies. There's under solar maps that can help you calculate these. NL has PV watts that effectively can help you deploy very quick calculations, like the hand calculation I was showing you. I will give you an example in the context of Toronto because I presented some calculations for Toronto, right? So in Toronto, a facade will receive about 1,100 kilowatt hours per square meter per year. Assuming that a BIPV module is 20%, that will be about 220 kilowatt hours per square meter per year for that vertical south-facing facade, assuming that has no receives no shading from surrounding buildings or trees. Now, how much less or more is that relative to a conventional PV module on your facade? The answer to that is, again, depends on what products you're using. Can be equal to a conventional PV system or less. And that less comes because your BIPV is not anymore optimized for solar generation. It's being optimized potentially for aesthetics because you're using it on your walls, can be optimized for demand side management. If you want to generate electricity, let's say in the morning, in the afternoon, you might want to deploy BIPV on your east and west facades. It depends on the color and texture of your BIPV. So if you are not able to see the solar cells, it doesn't look like conventional panel, and it looks like a color panel where effectively you can print your, let's say, your image on it. Then of course that compromises efficiency, and you can go anywhere between 22% efficiency of the module down to 10% efficiency, depending on the color orientation, texture, and so forth, right? So it can be a substantial reduction depending on the product you're utilizing. The long story short is that when you prioritize architecture and aesthetics, you're compromising efficiency, and the other way around.
One more, we had some new questions, but the last one I see in the Q&A is, what about recyclability of these BIPV?
That is an excellent question, and the recyclability is the same as conventional PV modules. We've seen recycling conventional PV modules we have an uptake the past 2 or 3 years. There are even companies that are specialized on recycling silicon-based modules, the same way we can recycle effectively BIPV modules. BIPV modules are not different in terms of architecture, material construction. So effectively is your glass, your solar cells, and your backseat. Your backseat could be some form of polymer base, so plastic recyclable, or it could be also another type of glass, right? So it's glass module. So in this case, everything is fully recyclable. There are a little bit more challenges when you use silicon-based modules, if you use cadmium telluride and so forth. These are solar cells that can be, or thin film, that are intrinsically deposited on the glass, and effectively it's very difficult to separate these two, if not impossible. And therefore, they're the same challenges as conventional modules, what kind of solar cell technology you're using. Nowadays, I'll dare to say 98% of BIPV modules are monocrystalline and polycrystalline silicon cells that are effectively fully recyclable. Now, by fully recyclable, again, there are components that effectively cannot be recycled, and there is, of course, a limit to the full. Maybe it's an exaggeration, but if you want to know more about that, there is an International Energy Agency report specifically on recyclability, and also some values that you can bring into your life cycle cost and circularity analysis. if you want to perform such an analysis for your building. So I highly recommend you to go and check that report that is effectively for all the countries members, and describes the processes and emissions and energy associated to recycling these technologies.
The Didier Thevernard is asking, it looks like in the applications you presented, the PV modules don't really protect from the elements. They are used mostly for generating electricity. Separate sheathing is used for weather protection. Are there cases where the PV modules themselves act as the weather protection, for example, solar tiles?
Yes, absolutely. So the facade, I just chose to present an easy application of BIPV, where effectively your BIPV modules is your cladding, right? And in other material, when you have that, if you replace your BIPV, let's say with precast concrete or composite panels or glass or aluminum, then again, these materials are your cladding, and then you need to have a weather barrier further in that protects your envelope component insulation, keep it dry and so forth, and airtight. So the approaches on rain screens is exactly the same. Now, for the roof applications, I believe you're referring to, because you say solar tiles, depending on the product that you're using, there's some products that effectively provide weather protection. So effectively is your primary and only water, snow, and ice barrier. But there are also products that are effectively they're playing a secondary role of the weather barrier. So effectively like a rain screen approach, where you have the ventilated cavity on the back for flushing your water and ice and so forth. And then there is your primary weather barrier, air tightness, vapor barrier, water barrier underneath, below your insulation, let's say, to protect your structure. So you can pick and choose effectively. There are different products, different capabilities. The more services the BIPV product, of course, offers, the more expensive it will be. In some cases, it could be also more challenging to deploy in existing structures, right? So effectively, if it's a retrofit, you want to do something that is easily deployable and cost effective. And these products that effectively provide the weather protection can be a little bit more cost effective, because there are gaskets to install, there's weatherproofing to install, and so forth. One last comment, all the projects that I presented effectively provide protection of your building from exterior elements, fully or partially. So effectively, all the projects that you've seen meet the definition of International Electrotechnical Committee and ISO standards of what is BIPV. They're not just conventional modules, what you saw. They're BIPV modules that play the function of a building envelope.
Dimitris Sosios is asking, how do BIPVs deal with dirt, dust, or snow? Are there any self-cleaning mechanisms?
Any self-cleaning mechanisms? So I will try to separate the two technologies the two applications that I showed you. So facades tend to, because it's glass, except it's heavily textured glass, most of the times rain is good enough, like a rain every 6 months, natural, processes, and humidity also cleans the facade. So effectively needs very little maintenance. Similar to a curtain wall system, every once or twice a year, you might want to go and clean your windows. And while you're doing that, you're also cleaning, your BIPV facade, and therefore this can, coordinate as a single maintenance action. When it comes to roofs, though, it's a little bit different. So effectively on roofs, you have the same challenges as any conventional rooftop PV. There are some adhesive state self-cleaning mechanisms, but typically if your glass is not heavily textured, again, rain should be able to clean your roof. Depending on the region you are, though, if you're like in a region that receives, I don't know, like sand from sandstorms, for example, near desert, then of course your percentage impact of your dirt and debris will be significantly higher. If you're near ocean, we also know that the generation will be reduced because the position of salt and so forth. So typically what we recommend is once or twice a year, you can go and wash your roof on the same, like incorporate that maintenance step with pressure, water, as you will be doing with your facade. And therefore, when you clean your facade, you can also clean your roof as a single maintenance step. I do not know another way. Potentially, I know there are a couple of companies that are looking to automate the process through robotics, but all these are still in demonstration stages.
Great. I think these are all the questions I'm seeing at, so we can slowly wrap up. I wanted to ask a final question. Oh, no, okay. I thought we got another one, but it was just a like. I wanted to ask a final question. So we're looking at BIPV, it's getting more and more common. We're seeing more projects now being implemented that before. What do you think are some future challenges that we have to face now with BIPV? We've already addressed a lot, but what is something that is coming up in the next years and we need to look for?
So if I had to choose two major challenges that we're facing right now in terms of BIPV application, the first one is regulatory challenges and, of course, training the industry. Suddenly, your entire building envelope is an energy generator, renewable energy generator, and then we need to rethink our bylaws and interconnections between building and utilities, because suddenly your buildings are generating energy, utilizing most energy on site, but they might be also exporting. You have electrically active envelope, roof, walls, and so forth. And then imagine you spend, let's say, $5 million in your facade, and then someone comes and builds right in front of it, right? Because there is no protection in terms of bylaws or regulations. So as we see these technologies taking off, and as we're heading towards electrification, decarbonization, enabling technology world, BIPV is one of them, right? Heat pumps is another one that ASHRAE is very aware of. We need to start rethinking how we plan and regulate access to the sun, how we plan and regulate bylaws, and who's able to do it, who's not able to do it, and potentially how do we proceed in terms of approvals for such systems. So there is a major gap here. There are countries that are a little bit ahead, such as Switzerland, Italy, and France, that they have incorporated some of these aspects in their codes, standards and regulations. There is also international standards and local standards, such as IC. I'm forgetting the number, but there is an electrotechnical IC and Canadian Standard Association standard, and UL standard that has set specific requirements for performance for BIPV. The second aspect is how do we incorporate now BIPV in our fire code? BIPV it's not particularly a component that will catch fire. So effectively, that's not the issue. The issue is how do we bring an electrical component into our analysis to being able to evaluate the fire resistance of our envelope. Also, because in the electrically active component, if firefighters, we need to access your building through the windows to break, let's say, your window, and that's an electrically active window, we need to be able to create a code and standard for immediate shut off of the system to isolate the system so you can enter the building for safety. And I saw at the same time Dr. Delil posted the international standard. Thank you, Veronica. 63092 is the standard international, and there is an equivalent Canadian CSA 63092. There's also an European standard, EN standard, under development. So the international community has identified these two gaps, and right now most of our work is focusing on standards, regulations, and bylaws, coordinating with the cities and regulatory bodies to incorporate BIPV in our list of products. But also we're going heavy on fire testing and impact of BIPV on the fire safety aspects.
Great. Thank you so much, Costa, for the great presentation and being so thorough with all the answers you gave to everyone. I think we can wrap up. We're 5 minutes early, but we we almost did the 1.5 hour. Yeah, so thank you everyone for coming to this webinar. It's gonna be I will be sending an email to everyone once the recorded version is uploaded on YouTube, so you can also watch it on demand and feel free to share with your networks. And hopefully we'll see you at the next one. Thanks. Thank you, everyone. Bye.